Hi, I'm Mark Wilson, the engineering heretic, and today I'm going to follow on to the third instalment in the injection moulding series, and I want to talk about high-speed moulding or high-performance moulding, and the equivalent of the Formula One sports car of injection moulding, and I'm going to talk about that and some of the implications about the tooling that makes up this part of the industry. Now, in some respects, this is referred to as the closures industry. In other words, tubs, containers, lids, and things like that. As you see before me, we have a part. It's an injection molded part. Now, this is an injection molded part. This one here is an injection molded part. There are some margarine containers and butter containers that are vacuum formed. You'll find that they don't have a clear a fine detail on the inside here. There are different sort of way of doing that, but this one here is injection molded. I want to talk about that and this alone. Now, as I said before, this is the sports car or the high performance molds that are around. Okay. This particular wall section, the reason why I say that is because, first of all, it has a very thin wall section. All of this is no more than about a half a mil in thickness all the way around. I think maybe the base might be a fraction thicker, but it is basically a very thin moulded part. It's like that for a number of reasons. Firstly, basically to minimise the minimum amount of plastic possible for this particular product. To keep that down so you don't have spending a lot of money on plastic. But the main one is purely performance. Now, in the past we've looked at some of the moulding parts and there have been quite thick wall sections, usually about 2.5, even 3 millimetres, sometimes even thicker than that. Mostly car components and things like that. And they have around about a 30-second cycle, and that's good enough for a car industry. If you make cars make 600 a day, you can easily keep up with that. In the closures industry, things like this particular tub here, they will want hundreds or thousands an hour from these particular tools. So they need to run exceptionally fast and have a number of cavities to make this work. And when I mean exceptionally fast, I mean down to around about 3 seconds. So when this runs in the machine, it's running, there's a core here on this side of the tool, the equivalent of the moving soft tools on this side of the tool here. And of course, there's a hot runner system off the back. We'll talk about that system in a minute. But this particular mould will have no ejection system like pins, round pins that pop things off and things like that. There's none of that. What it relies on is basically air pressure to pop this particular part off. So when this mould opens up, there's a section in here that will basically pump air into the cavity. And because it's such a thin wall section, there's a little valve type thing in the bottom here that lifts off under air pressure. And because it's such a thin wall section there, it basically just pops off almost immediately. So when these particular molds run, they almost look like they're they look non-hydraulic for a start. They look like it's a mechanical thing that's running because the cycles are so fast. This thing closes and opens and closes and opens in a 3-second cycle. And when it opens very fast. And on the back of the machine, there's a couple of molding machines. One of them is called the Nestor machine. There's another one that does specialise in high production moulding cycles and things like that. The Nestor one's the one I'm most most familiar with. And at the back of the machine, as it's running, they run so fast. These plattens are moving so fast, it just makes your head spin. But at the back of the machine, there's a whole bunch of, it's hydraulic, but there's a whole bunch of accumulators at the back of the machine there, storing up this hydraulic energy under immense pressure and running this machine kind of beyond what you'd expect from hydraulics. And of course, it would pump the plastic in the back of it. It would freeze off almost immediately, open up very quickly, air blast the part out there, and it would fall out at lightning speed and land in the bottom of the machine and be taken away used on a conveyor belt. So that leads us to a number of issues with these particular products. One is, let's deal with the first one as well. On the back of this particular moulding here, this is a hot runner system. The plastic will run along a runner system and then down onto the centre of the part. There will be there's a round section here, and there's a little dimple or a little blemish. It's more of a circle here, not like other hot runners which leave a blemish. Because this wall section is only half a mil thick, we can't allow this blemish to basically make a fault in the moulding area. So this has a particular gate called a valve gate. That is a little valve that basically closes off every shot, and when the mold closes, it will basically open up the valve, shoot the plastic in really quickly, okay, close the valve off, sealing that off, making sure that there's no vestige or anything like that left there, and that way there's no real flaw in the centre of the part. So that's one thing that makes this thing a high-speed moulding product. They're expensive to do. Right, the other thing too is cooling. Now, it's not so much of a problem on the what they call fixed side of the tool, in other words, this side of the tool ground here, because you can get waterways around fairly close to the cavity area. That's not much of an issue. On most of the core, this area here, you can run cooling things up in here. But the problem is the centre core here, this area in here, that because it's moulding so fast, steel or whatever this is built of will not remove enough heat to get out of this area here from the core. And if you're a tool maker, the first thing you do when you pick up a product like this is you run your finger down the side here, and usually about a third of the way down you feel a very small seam. Okay, that's about a third of the way down. I can feel that just there. There's a little seam there. And you feel that runs all the way around here. So there's something going on in this last third of the core on this particular product. And that's because that part of the core there is made of beryllium copper. Beryllium copper is a hard version of copper, very difficult to machine, almost impossible to EDM. But the reason why they're using beryllium copper is because it withdraws heat very quickly. You don't have to have much water flowing in the beryllium copper core before it will just suck the heat out of that very quickly. Sometimes we call them high performance cores. So this section here has a beryllium copper insert on the top of it that basically withdraws this heat. It's not so much of a problem down deeper on the core, but it is on the very top of the core, the last third. Now, there's other things going on here when it comes to these particular tools. First of all, let's just do I've got a bit of a sketch here. Okay, we'll go in a little bit closer and see this a little bit closer, and I'll just explain what goes on here. I'll zoom in just a little bit. Right. There's a very, very rough sketch of this wall section of this part here running down through here and across there. So, on the core of this doll, let's put the shut face, or where the mould closes, which is this area here. There is a flat face coming out there and a flat face coming out there. Okay, so all of this area here is the core area, and this area here, this is the cavity area. Okay, there is a valve gate which runs in a little valve. I'll put the little valve gate in here. It looks more like an ejector pinhole, but there's that valve gate coming down there, preventing that vestige or a flaw in the bottom of this tub here. Okay, there is a core across the third here, which is beryllium copper. Okay. Now, this must be locked in place because there's a huge amounts of pressures on these particular moulds. This core has to also reach down and across, and usually a tapered angle here, across here, and then back up again. to lock this in. So that's all part of this core here. And of course that will proceed around there. And there will be a number of cooling wires running up and connecting up with galleries in the beryllium copper core. So that's with that, and that will also assist in cooling this area here. But that top bit there is the bit that's really, really critical. There's a few more things going on here as well. We also need to have a air popping system. So inside of this core here, there's normally a little valve thing built into the beryllium copper core in this section here. It's a little valve shaped a little bit like that, and it has a spring on the back of it, and just a little bit of air pumped in there. One will lock off on the outside here. A little bit of air will lift this up, blow this around here, and pop this part off very quickly. We don't normally do stripper plates or things like that, which is a different form of ejection because it's a mechanical thing. And at a 3-second cycle, there is no time for anything mechanical to move other than the mold opening and closing. Now there's further problems going on here. When you build these types of molds with a 0.5 or half a mil 40 thou wall section, 0.5, the precision of your mold increases dramatically. If there's any error in the thickness of this particular part here, supposing that was 0.55 there and 0.5 there, that's only 2 thou or 0.05 of a millimetre difference. The mold pressure, because this is a thicker wall section, will stay molten longer, and it will actually cause this core to shift off to the side. You can't just rely on this die closing like that and guide pins just lining the thing up. You must lock this in and prevent this core from shifting on the mold itself. So any slight variation in the wall section will cause, if that was slightly bigger there, will cause that to stay molten longer. The pressure will remain in that, and it's usually about 2,000 pounds per square inch mold pressure or something similar to that. And it will cause that core to shift off to the side there and make any small error far worse. In other words, every time you mold this thing, it will shift off. So what you have to do is make sure you build this mold as accurately as you possibly can. 0.005 is the sort of tolerances you need, which is basically a quarter of a thou in the old scale of 2.5 tenths or something like that. 0.003 or something like that. You need to chase every size you possibly can here and chase them down as accurately as possible. Now, during the course of this mold running, we also need to lock this core in with the cavity. So on the shut face, we actually run this up on an angle up here, and that will run the perimeter of the mold. So it'll be down in a dip, then it will run across here, and there is a locked in area here, basically a wedge block built, or four of them on all four sides of the corners of the mold. This wedge block here, which you bolt in from the outside here, that fit in there, that lock this core, this cavity block into its bolster. So it'll go up here as well and across here and basically lock into the bolster as well. Now, over time, we get this runaway effect. Over time, for some reason rather, it will, over time, start to wear a little bit. These wear plates here, they're a separate wear plate. They're expendable, so you can remake them. They're usually bolted from the outside, so you can get in them quickly. And if for some reason rather these plates wear a little bit, the slot will allow this to core shift. So what we need to do is be able to adjust these, and normally over time you will have to put a little bit of shim behind the sides of this to lock this further in, and basically measure the part all the way around find out where the errors are, and then basically shim the wedge blocks to counteract that. But it's a runaway effect, because once this thing core shifts over or locks and moves out and puts a lot of pressure on that every time you open the mold, it will put pressure on that, and of course the other side will hardly be touching. And when you open that there, it will scuff up on the face there and wear even faster. So it's a runaway effect. If you don't chase this down, it will get out of control. And before you know it, you could be having almost no wall section on one side there and mill on the other. It'll shift off that much. So that's a single cavity die. It becomes even more difficult when you're building one of these for 2 cavities. I'll just have a look at that as well. A 2 cavity or a multiple cavity, normally you'd want at least 2 for this. A single cavity would be terribly slow. What you want is a multiple cavity. So let's put in, we have a tub up here, one tub there, and we have another tub here. I'll just do this quickly, and so on. So then you can have another one behind that as well. So of course we've got there our shut face going up across here. And what we do is put this on a separate bolster. There's a big plate across the back of this mold here. These are bolted, these particular inserts are bolted to a main back plate, and they're kept separate. And of course, on the other side of the tool, there's your main insert there. They can be separate, or they can even be in the solid. Normally, we separate them as well through down here. Sometimes we put them in the solid, sometimes we don't. Depends on what size and everything. So there's my cavity. This is my core area. My molding is in around here. A bit rough and ready, but anyway. Okay, so we have our runner system coming through the back of this plate here, the insert, down onto the cavity. We have our beryllium copper core here, and we have our popper valve here to get that off. So these are all on separate plates, and they're guide pins and bushes into the die set. Now, the reason why we do this is because you need to have each of these cavities, how many you've got, on separate blocks here, so that you can adjust the wall section for each one. So what you do is you back off the main bolts and hold these things in place. You shim these areas here. You shim them to correct the errors as they happen over time. Originally, you set the mold up, you build as accurate as you can. Normally, they work perfectly for a number of, for many months. But then, of course, these little wear things will start to wear. But when you shift that one, the other one might be different. So you need to have it on a separate block so that you can move this one around independently of that one. And that's another thing you have to do when you build a high-performance mold like this for margarine containers and what have you. They're fascinating to watch, these things, and they really are just mesmerising to see them run. They run so fast. Normally, they put them in a production line, so they'll actually have this running where they're making, this is butter, this one here, or margarine or something like that. At the production site where they're making the product, they will mould these on site, built into the production line, and have these going into tubs. And of course, you don't have to worry about you take them straight from the mould, straight basically on the production line, and you're using it almost straight away. So you don't have any stock or anything like that in-house normally. You can mould them elsewhere, but then you have to truck them to site. So that is high-performance moulding, kind of thing you would see for containers and all sorts of things. There are other types of closures. There's blow moulding and things like that, but these ones here are particularly injection moulded. There's a couple of reasons that I was explained before, but you do find a very defined inside here. You feel this little seam on the side here, which is a dead giveaway that's injection moulded. And there's also, if you looked underneath the steps, there's a little round little ring there of the where the part is injected through a valve gate. And that is high performance moulding. And I'm Mark Wilson, and thanks for watching.